Hi, today's lesson is section 5.2, logarithms. Now, logarithms were invented around 1600 by a wealthy Scotsman named John Napier, and he was interested in astronomy among other things. And in astronomy, you have very, very large numbers, and sometimes you need to multiply them, and sometimes you need to divide them. And the calculations were very overwhelming for John Napier and his staff. So he invented a technique for easing the calculations. And his thinking went like this. If you have really big numbers, it's tough to multiply them. But if you could express those really big numbers as powers of 10, well, then it's easy to multiply them. As we know from exponents, you just add your two exponents and you have your answer. But the problem is, well, how do you convert really big, messy numbers to powers of 10? He had a staff of people working on calculations. Of course, everything in those days was ink on paper, so it went very, very slowly. These people were all in a room and they painstakingly figured out all these different roots of 10. Like, what is 10 to the 0.0001 power? Then what is 10 to the 0.002 power? So on and so forth, all the way up to 0.99999. And they eventually got it done, and it worked very well. It saved a lot of time and effort. In our lifetime, well, in my lifetime, this was still used. Since calculators didn't become commonly available to the 1970s, people used devices called slide rules sometimes, which you could carry around with you. And the slide rule was actually based on this concept. So you could do calculations really fast if you knew how to work that slide rule. Okay, so that's a little bit of background just to show you where the stuff comes from. It's always good to see where it comes from. For us, we just studied exponential functions. Y equals b to the x is the standard form. So the exponential function is 1 to 1, which implies that it has an inverse. Every function that is 1 to 1 has an inverse, and vice versa. So if we just reverse the variables, instead of y here and x there, we just flip-flop them, we have a statement that says this, where y is our input, x is our output. That's a function. And in fact, this function gives us our definition of the log function. Y is equal to the log of x base b means that x equals b raised to the power y. So b is our constant, of course. X and b both have to be positive numbers for this definition to make sense, and b cannot be equal to 1. As we saw with the exponential functions, we don't bother talking about b equals 1. It would just not mean much and things would get messy. So you could take an exponential statement like this, which we've been looking at now for a week. You could express it as a log statement. This is the same as saying that 3 is my base, 9 is the number I'm taking the log of. So to get 3 taken to a power to be 9, that power would have to be 2. So this is just another way of saying this. They are both mathematically equivalent statements. So this one here, we know this is true. This says that the log base 4, there's our base, of the number 1/4 is equal to -1. It just says that if you take 4 to the power of negative 1, you get 1/4. And that's what that says. All right, let's get the eraser. There's a couple more in there. This is, of course, is example 1 on page 327, or perhaps we're around 328, I'm not quite sure. In part C, well, we certainly know that if you take a number like 5 to the power 1, you just get 5 back. How would you make that same statement in logs? You would say the log to the base 5 of the number 5 equals 1. This just says that 5 to the power 1 equals 5. In part D, we're given the exponential statement x equals 3 to the y. So this just says the base is 3, the exponent is y, the number you end up with is x. 3 to this exponent gives you x. Let's look at example 2 where we go in the other direction. Here we're asked to take a logarithmic statement, a log, such as this, log base 2 of 16 equals 4. That is a true statement. Write it in exponential form is what we're asked to do. Okay, this tells me that the base 2 to the exponent 4 equals 16. Again, an equivalent statement, just says the same thing. In part B of that example, the log to the base 10, and this is the kind of statement that Napier would have been interested in. He was interested in the base 10. Of 0.0001 equals negative 4. What that says is that the base 10 taken to the power negative 4 gives you 0.0001. And in part C, log base 6 of 1 equals 0. What that's telling you is that 6 to the power 0 equals 1. And we know that's true for any non-zero number, including 6. Now, that's how we convert back and forth. Let's calculate a few of these. Example 3 says evaluate this. In part C, let's go straight to part C. What is the log of 8 to the base 2? Well, I notice that 8 is a power of 2. I know that 2 to the power 3 equals 8. So what this is saying is this function returns the exponent, which when operating on the base 2 gives me the number 8. So that's the exponent, 3. This is true since this is true. In part D, log base 4 of 1 over 16, what does that equal? Well, I guess I could write the word since in here if I wanted to make a total explanation. Well, how does 16 relate to 4? How does 1 over 16 relate to 4? Well, I know that 16 equals 4 squared, right? Therefore, 1 over 16 is equal to 4 to the negative 2. Yeah, that's right, we've seen that before. So, since the base raised to the exponent negative 2 gives me the number I'm taking the log of, that must be what this log value is. That's the exponent. That works. And then in part E, let's make a little room for that. In part E, log base 10 of 0.001. What does that equal? Well, I know that, I'll put some ditto marks there, since 0.001 is equal to 10 to the negative third, right? 3 decimal places, negative 3. And I know that this is the same as 1 over 1,000, which is the same as 1 over 10 to the third. They're all the same, right? Well then, this is telling me that if I take the base 10 and I raise it to the power negative 3, I get the number I'm supposed to get. So this equals negative 3. Now, why don't you practice with a couple of these? On page 340, do number 1, and then do number 12, parts A, B, and C. Okay, we'll come back in a couple of minutes and see how you made out. Okay, let's check this out. In number 1, you are asked to take y equals the log of x base 3 and write the equivalent equation in exponential form. So this says that 3 to the power y equals x. So that's the answer in number 1. In 12, part A, you're asked to find the log of 64 base 2. Well, since 2 to the 6th equals 64, 6 is that exponent that you need to raise to get 64. So this log is equal to 6. Then in part B, you're asked to evaluate the log of 27 base 9. So one way you can do a problem like this, and your book does it this way, is you can say, all right, let this number I'm looking for be equal to y. That's the same as saying that 9 to the y equals 27 if we transform the log equation to its corresponding exponential equation. Now, 9 and 27 are both powers of 3, so this says that 3 squared raised to the power y equals 3 cubed. Well, I can just multiply my exponents, right? 3 to the power 2y equals 3 cubed, so the exponents must be equal. 2y equals 3, solve for y, and I get y equals 3 halves. And then finally, 12c, we're asked to evaluate the log to the base 4 of 2. Well, I could say let this equals y and then work like I just worked that last problem. Or I can just make this observation. Since the square root of 4 is equal to 2, and 4 to the 1/2 is equal to the square root of 4, then I see that the exponent I need is 1/2. So I say that 4 to the power 1/2 gives me 2. Yeah. So that's how I can evaluate that expression. Now, let's look at the graphs of these functions, because we're always interested in graphs, right? That's the beautiful thing about analytic geometry, which is a lot of what we're doing this semester. Whatever you see in the numbers, you will see in the graph, and vice versa. On page 329, look at example 4. It talks about the function y equals the log of x to the base 2. Now the equivalent exponential form of this function is x equals 2 to the y. If we just pick out some random y values and calculate the x values, we get these ordered pairs. If we fill in the curve, it's going to look like that. Sort of looks like the exponential function because, you know, it's asymptotic and it kind of flies away like that, but it's flattening as it flies away. But it never goes down, just doesn't go, it goes up at a slower and slower rate as it goes off to positive infinity here. And in fact, it should look like the exponential function because this is the inverse of an exponential function. Y equals the log of x to the base 2 is the inverse function of y equals 2 to the x. Now remember, when we looked at inverse functions, and we looked at graphing inverse functions in particular, we said, oh, the inverse is always symmetrical to its original function, flipped about the 45-degree angle, which is the line y equals x. So that means this. We did look at that graph, y equals 2 to the x, and it looked like that. And you can see that if I flip this green curve over, that dashed line, it's going to land on my black curve here. All right. And finally, we have something called, finally with the graphs, that's the final thing I should say for right now. This is the case when the base is greater than 1. Okay, here it's 2. You're always going to have that general shape. But remember, the base can also be between 0 and 1. For those, you sort of get this black curve flipped upside down, right? Because you're dealing with fractions as your base there.